which is about thunderstorms. Now, I just want to state at the beginning of this video that this is actually the first of 3 chapters that are going to focus on thunderstorms and severe weather. And while we're going to talk about severe weather a little bit near the end of this video, this particular chapter is a generic chapter about thunderstorms. So it's not really a severe weather chapter. When we get to chapters 14 and 15, those will be the chapters that focus on severe weather, where chapter 14 will be about severe weather in general, and chapter 15 will take a closer look at tornadoes. So this is just kind of an introduction, just getting our feet wet before we get to severe weather in chapters 14 and 15. So let's start the slideshow. Excuse me. There we go. All right, so this is just basically a black and white satellite image of various types of thunderstorms. And this is over Indiana, Ohio, and Kentucky. And you'll see, if you look carefully, that there is a lot of detail actually in this particular image. So you can see that we have a cumulus field where we have just a lot of little dots of grayish white clouds. Remember, this is again a visible image, so we're looking at albedos here. And then you can see that we have some better described images right here where we have towering cumulus clouds. And then where you see kind of this more puffy white looking area, these are actual thunderstorms. And if you look carefully from the thunderstorms, you'll see that there's some areas of roughness where there's a little bit of bubbliness. And these are where our most intense thunderstorms are actually occurring. So thunderstorms are not necessarily occurring beneath this entire area of cloudiness. A lot of this is anvil cloudiness, which is actually spread out by the upper level winds, but it's not actually raining. So you have to actually take a look for the rougher cloud tops to indicate where the thunderstorms are actually occurring. So you can really see, given the detail that we're able to get from a visible satellite image, you can really see where the towering cumulus are located, where the thunderstorms are located, the obvious anvil clouds being spread up at the upper level winds, and then the more generic and benign cumulus field that is occurring on this day. And you'll also see some areas of stability. If you take a look at northwest Ohio here, you'll see that there's not even actually a cumulus field at all. So this area probably had some thunderstorm activity relatively recently that stabilized the atmosphere. We'll talk about why it is that thunderstorms stabilize the atmosphere as we move through this video. But you can actually see pretty well behind where there's thunderstorm activity. You can see there's actually no cumulus field at all, indicating that the thunderstorms have stabilized the environment and you can't even get enough convection for cumulus clouds. All right, let's just move on for a little bit of climatology. And this is basically showing us the average number of thunderstorm days across the United States. And you'll see that right here in northwest Ohio, our average basically straddles 40 days a year with thunderstorm activities. I'm actually making this video in the summer of 2023, and we're having a very, very unusual summer because we've had virtually no thunderstorms this summer so far. Today is July 15th, and in fact, there have been very, very few thunderstorms this summer. And if we continue the way we are, this year, 2023, our total number of thunderstorms will fall well, well below 40. As a matter of fact, I would imagine it'll fall below 20, at least here in my part of northwest Ohio where I live. If we take a look just again at the climatology, you'll see that the northeast and the western parts of the country are where climatologically the smallest number of thunderstorms occur. And you can see right along the coast of New England and particularly along the Pacific coast, the numbers actually fall below 5. On the other hand, if you move to Florida, you'll see that they actually hold the crown for thunderstorms. And then just inland in southwest Florida, west southwest Florida, you'll see that there's a little area that averages more than 100 thunderstorm days per year. Now, this does not line up with maximum number of tornado days. It is just maximum thunderstorm days. We'll see when we get to chapters 14 and 15 that the maximum number of tornadoes per 10,000 square miles actually occurs in the middle part of the country, in Tornado Alley, which is kind of where you would expect for it to occur. Now let's talk about how we basically get our thunderstorms. Now there are a number of ways that we can get thunderstorms, but what we basically need to do is we basically need to figure out a way to get a parcel of air to a point in the atmosphere in terms of its vertical movement where it becomes warmer than the surrounding environment and then can accelerate upward on its own. So we're basically looking for a way for the atmosphere to be unstable. Now what I want to do is I want to point out two important levels in the atmosphere when it comes to thunderstorm development. And you'll notice I have the word convective here, and we'll get to convection in a minute. So the first level, which I have right here on the right-hand diagram, is called the lifting condensation level, or the LCL. The lifting condensation level is the level to which a parcel must rise in order for the parcel to become saturated. So from the surface, if we talk about a surface-based parcel, the parcel will rise and cool dry adiabatically as long as the air inside the parcel is dry or subsaturated, and it cools to its dew point right at the lifting condensation level. So the lifting condensation level is the level at which a rising parcel saturates. Now, if the parcel continues to rise, what will happen is it will eventually reach a level in the atmosphere called the level of free convection, or the LFC. And the level of free convection is the level at which the parcel and the environmental temperature become the same, and above which the parcel will become warmer than the surrounding environment. Now, once the parcel reaches the lifting condensation level, if it continues to rise, it'll cool at the moist adiabatic lapse rate because the air inside the parcel is saturated. So as the parcel continues to rise and cool at the moist adiabatic lapse rate, we will get condensation of water vapor and cloud development and the release of latent heat. And this reduced rate of cooling, if the parcel continues to rise and the environment cools relatively rapidly, will allow the parcel to eventually become warmer than the surrounding environment and then to accelerate upward on its own. The level of free convection is the level at which the rising parcel becomes the same temperature as the environment on its way to becoming warmer. So it's the level at which rising parcels become warmer than the surrounding environment. Okay, so let's take a look at what this appears like if we just take a look at clouds. So again, important levels for convective development. The lifting condensation level, again, it's the level at which rising parcels saturate. And if you take a look at these clouds really carefully, what you'll notice, as we all know with cumulus clouds, is that they kind of have this bubbly appearance. But if you take a look at the bases of these cumulus clouds really carefully, what you'll note is that the bases are actually pretty flat. And so what's going on here is that we have parcels that are rising from the surface, so we're getting surface-based parcels that are rising as a consequence of convection, and what's happening is they're cooling at the dry adiabatic lapse rate, and then at the lifting condensation level, the air in the parcels becomes saturated, and any additional lift will cause condensation and cloud development. And so this really flat cloud base is the floor at which our condensation is taking place, and so this is our lifting condensation level. Below it, the air is still dry, no clouds. Above it, we have condensation occurring in rising moist parcels, and we have a cloud. And this flat base indicates a lifting condensation level where this condensation begins. And again, if you take a look at all of the cumulus clouds that are developing in this field, you will see these flat bases indicating a really well-defined lifting condensation level. Now, when the atmosphere is unstable, you will see this bubbly appearance in our cumulus clouds, indicating really rapid vertical development. Now, not every cumulus cloud, even a rapidly developing cumulus cloud, will ultimately produce a thunderstorm. Sometimes this is as far as it gets in this picture, and that's it. So we basically have a well-developed cumulus field, and that's the end of the day, no thunderstorms. Now, if parcels have enough upward motion to actually make it to the level of free convection, then you'll see much, much greater vertical development. You'll see really, really explosive development. It almost looks like a bomb exploding when you take a look at these very, very rapidly growing cumulus clouds. So once the parcel reaches the level of free convection, it tends to accelerate up very quickly because it's more buoyant than the surrounding environment, and you get this really rapid development and this very, very bubbly appearance to our towering cumulus clouds. Again, if you take a look at the base of this towering cumulus, you can still see the well-defined lifting condensation level. So let's continue focus on convection initiation. So we get convection on lots of days. So there are lots of days where there are no thunderstorms, and we simply get a cumulus field where the cumulus clouds have developed to some extent, where you might only have small puffy cumulus clouds on a day. You might get better vertical development, and then on days you might get a full-blown thunderstorm. So on many days during the summer, particularly on hot, humid days, our thunderstorm development is pretty much driven by convection. And we get this convection through a couple of steps along the way, and the sequence is important here. So the first thing that happens is that we simply get the sun shining. And so we get energy coming down from the sun, Remember that the Earth's atmosphere is pretty much transparent to the visible energy that is coming in from the sun. So about half this energy, it reaches the surface on a clear day. About half of it gets bounced back out to space. The other half is absorbed at the surface. As this energy is absorbed at the surface, the energy is transferred to the surface, and so the surface becomes hot. As a result, the surface will then heat the air above it via conduction. So this is number two. So number one is radiation, number two is conduction. And so remember, and this is from Weather and Climate and also from Weather Studies Laboratory, but I mentioned it, I believe, in the Chapter 9 video. Remember that air is a really awful conductor of energy. So the Earth heats the air above it, the lower atmosphere, via conduction, but this warming does not actually extend very high up above the Earth's surface. So the air above the surface gets hot, but the heating does not go very high up. And as this air is heated, it also becomes more buoyant. It expands and becomes more buoyant. So again, air is a poor conductor of energy. And what happens is that because almost all of this heating is concentrated, fairly close to the ground, what we see in terms of our sounding, in other words, of our vertical temperature profile, is that our morning sounding goes from being pretty stable to being pretty unstable. In better words, the environmental temperature begins to decrease very rapidly with height, our environmental lapse rate becomes large, and the atmosphere becomes unstable. So we get surface-based instability. Now what this means in the context of buoyancy of our air is that the air near the Earth's surface becomes pretty buoyant because it's hot. And as a result of that, this heated air will begin to rise via convection. So the warm air will rise as a result of convection. So convection causes particles to rise. Here's number three. And then I have a note to myself to discuss the justification of this adiabatic requirement that I developed in Chapter 9. So you remember in Chapter 9 that I discussed the fact that parcels pretty much behave like balloons in terms of our first two requirements. So they have flexible boundaries, and there's no mass exchange between the air inside the parcel and the surrounding air in the environment. And what distinguishes a parcel from a balloon is the fact that our parcel boundary, our elastic boundary, is adiabatic. In other words, we do not allow any energy exchange across the parcel boundary. So the total energy inside the parcel is fixed. It's held constant. Now, obviously, we do not have a lot of balloons just floating up and down through the atmosphere. This is air, and air, as it rises, kind of has these fuzzy boundaries on it. But air does mimic parcels. The whole reason why meteorologists use parcels to assess atmospheric stability is because when air rises through the atmosphere, it actually does a pretty good job of maintaining its contiguous shape. And so while the boundaries of the parcel or a rising volume of air are fairly diffuse, the reality is that rising volumes of air do maintain their integrity for a good distance as they travel upward. And because air is a terrible conductor of energy, we can maintain this total energy requirement inside of a rising volume of air. And so rising volumes of air in the real world do mimic this adiabatic requirement that we have for parcels. Okay, so what I'm going to do now is I'm going to move on and talk about a couple of different types of thunderstorms. Now I'm going to start with talking about two types of thunderstorms that are triggered by thermal or temperature gradients. And then I'm going to move on to a definition of wind shear and talk about thunderstorm organization as a function of wind shear, which I know is going to be really important to the students in the class who are trained to be pilots, which is almost everyone. So you're going to really want to pay attention to everything I'm moving through next. All right, well, let's start with thunderstorms triggered by local thermal gradients. And there are going to be two types of thunderstorms. Now, as I say two types of thunderstorms, just remember that a thunderstorm is a thunderstorm. So when I say two different types of thunderstorms, what I'm talking about are two different mechanisms that are driven by thermal gradients that lead to thunderstorm development. The first type of thunderstorm that is triggered by a thermal gradient is a sea breeze thunderstorm. So anybody who has gone to one of the Great Lakes or to the ocean or the Gulf of Mexico during the summertime knows that a sea breeze typically kicks up during the afternoon hours. And so this is a breeze that comes in from the water, and it tends to cool things down a little bit. The sea breeze also tends to kick up thunderstorm activity a couple of miles inland from the shore, from the coastline. So what we're going to do now is talk about why sea breezes actually lead to thunderstorm development. And so I actually had this set up right here in this graphic from the book, and so let's actually go through it. The whole reason why we get sea breezes is because there's a disproportionate heating of the land surface versus oceans during the daytime hours. And so the disproportionate heating of the land surface, so the land has a very low heat capacity, which basically means that as it absorbs energy from the sun, it warms up much more quickly than water, which has a much higher heat capacity. And as a result, even though it's absorbing the energy, it doesn't heat up as quickly. So during the afternoon, the land surface gets hot and the water stays pretty cool. So as a result of the land surface getting hot, what happens is that the air expands, the column expands, the mean column temperature in the lowest part of the troposphere increases and heights increase. And you'll notice here that I'm talking about upper level heights. I'm talking about only going up to about 925 millibars. So this is a pretty shallow phenomenon that I'm talking about here. But we get higher heights over land than we do over the water. So what this does is it triggers a horizontal pressure gradient at upper levels at 925 millibars, where the pressure gradient is directed from land to water. And as a result of that, what we will do is we'll get a wind that develops at 925 millibars that basically is blowing from land to water. Now keep in mind that this is a pretty small scale phenomenon. So we're talking about the circulation that may only be 5, 10, 15 miles in terms of its length. And so the Coriolis force really doesn't come into play here. The air pretty much blows at 925 millibars directly from land to water. Now, as we remove mass from the column over the land, because we're moving air from land to water, this will lead to the formation of a pretty weak center of low pressure along the land, or just over the land. And so we're actually forming low pressure at the surface over land. Meanwhile, we're adding this mass to the column just a couple of miles offshore over the water, which leads to the formation of weak high pressure or higher pressure over the water. So mass addition over the water leads to weak surface high pressure. We get a pressure gradient at the surface now that is directed from water to land, and the air begins to blow from water to land. And this is our sea breeze. Now the sea breeze, because the air originates over the water, this air is cooler than the air over the land. So what we're doing is we're pushing cooler air onto the landmass. And so this is why sea breezes actually are kind of refreshing, and they bring the temperature down a good couple of degrees during the afternoon when they form. So we get our sea breeze. Now, I'm not changing any of the writing on the right-hand side, but I'm changing the picture a little bit. And so what you'll see now in this picture is the sea breeze is depicted as being blue and cooler, and you'll see that the sea breeze is a fairly shallow phenomenon, excuse me, in terms of the boundary between the cooler marine air and the warmer air above it. And the boundary of the sea breeze is what we call a sea breeze front. And so it acts like a mini cold front. The air is a little bit more dense, and what it does excuse me, is it pushes the warm air upward. This air is already probably rising on its own because of convection, but what the sea breeze front does is it gives the air a bit more of a vertical kick upward, which might actually get the air to reach the level of free convection. So if the air reaches the level of free convection, then we're off to the races, the air accelerates upward, and we get our thunderstorm. So the sea breeze acts as a mini cold front, and excuse me, we get thunderstorms. My throat's a little dry here, so I apologize if I'm coughing a bit. These are clearly not professional audio events when I make YouTube videos. Anyway, moving forward, here is a picture. This is infrared enhanced, so people are actually enhancing this color. I promise you that the land surface over Florida is not red. This is Lake Okeechobee, and this is the coastline of the Atlantic Ocean with South Florida. And what you can see if you look really carefully is you can see this line of thunderstorms right here, just to the east-northeast of Lake Okeechobee. And these are thunderstorms that are forming along the sea breeze front during the afternoon hours. And you can see here we have a little bit less, or it's more diffuse sea breeze front, making a little bit further inland. And so you can see a little bit more of a dotty kind of scattered nature to the thunderstorms and one big one right here. But you can see the sea breeze front really well right here. And I want to make clear here also that you don't need the ocean, the Gulf of Mexico, or Lake Erie. You don't need a big body of water to get this phenomenon occurring. If you look really carefully along Lake Okeechobee, you'll see a line of clouds right here on the western side indicating that we have a lake breeze front. And I've even seen examples of these sorts of lines of clouds forming just inland from large rivers like the Mississippi River. So rivers can even form this phenomenon. So you don't need a really big body of water to form these frontal boundaries that are resulting from thermal differences between air coming off water and it pushing air that is located over land. Okay, let's move on to the second type of thunderstorm that is triggered by a thermal boundary. And these are called valley to mountain thunderstorms. Now, what we have in this situation is we have a mountain, and these are typically the Rocky Mountains, although we see this over the Appalachians during the summertime a lot as well. Now, what I want to point out, and what this picture doesn't really show well, is that on flat surfaces like the Great Plains or most of western Ohio, even during the middle of the summer, the sun is actually hitting the Earth's surface at an angle. So during the summer solstice here in northwest Ohio, the sun is typically at noontime about 60-65 degrees high in the sky. So the sunlight is still coming out at an angle. And in fact, the sun is never directly above our heads in this part of the northern hemisphere. It only happens between the Tropic of Cancer and the Tropic of Capricorn. If you're out of the tropics, it doesn't happen. Now, as a result of the energy from the sun hitting a flat surface at an angle, what this does is it causes the energy from the sun to be spread out a little bit, relative to if the sun were directly overhead and shining straight down. Now you can prove this to yourself by just simply taking a flashlight and holding it above a tabletop. And if the flashlight is shining straight down, you'll see that it just makes a little circle of light. And then if you begin to angle the flashlight along the tabletop, you'll see that that circle begins to spread out into an ellipse. And so the energy is spread out over a larger area. So on flat surfaces, even in the middle of the summertime, the energy from the sun is spread out a little bit because the sun's energy is hitting this flat surface at an angle. Now, if you have a mountain, what will happen is the sun is still coming at the same angle, but because the surface of the mountain is also angled, in better words, you can have a fairly steep slope of a mountain, the sun will actually hit the mountainside at a 90-degree angle, and the energy will be more concentrated when it comes in. And so what happens is you'll see that along steeply pitched slopes of mountains, so again, this is primarily in the Rockies, but you do see it in the higher elevations of the Appalachians as well, is you'll see that you get disproportionate heating along the mountain slopes relative to the plains. As a result, it gets hotter along the mountain slopes, and this leads to slightly higher heights over the mountains than over the valleys. And so we end up getting the same type of phenomenon that we have with our sea breeze circulation, which is that we'll first get a pressure gradient that points from high to low pressure, in other words, or high to low heights. In this case, it'll point from the mountains toward the valley. So you get increased upper level heights over the mountain, and you get an upper level pressure gradient force and wind from mountain to valley. So now what we're doing is we are removing mass from the column over the mountain, and we're adding mass to the column over the valley. So we'll end up getting surface low pressure over the slopes of the mountain and surface high pressure over the valley. And so as a result, we end up getting this sort of a circulation. Again, we get a cellular circulation where during the midday and afternoon hours, you'll see that at the surface, where we've actually added mass and created high pressure, we'll get winds blowing in towards the mountain and then up the sides of the mountain. So as this air rises up the sides of the mountain, we're also, again, probably getting convection due to the intense heating from the sun, is that this extra little boost when we get air actually moving up the sides of the mountains might be enough to actually push a parcel up to the level of free convection so that we can get a thunderstorm. So just moving through the wording, mass addition over the valleys leads to weak surface high pressure. The surface pressure gradient force is directed from valley to mountain. We get upslope winds and thunderstorms. So here is going to be a 3-picture sequence of the central Rocky Mountains. So going from southern Wyoming through Colorado and into New Mexico. If you take a look real carefully, the Rocky Mountains, the higher elevations of the Rocky Mountains are darker. This is where we have heavy forested areas, whereas in the plains, we typically don't have much in the way of trees. And so you can see where the high mountains are just based on the darker shading and the lower albedo of our forests. So this is early morning. If we go to the early afternoon, what you'll begin to see is we get cloud development, which is pretty much going on all over these higher elevations as we begin to get air flowing up the sides of our mountains. And then later in the afternoon, you'll see that we get thunderstorm activity, which is again occurring pretty much over all of our higher elevations. And this phenomenon plays itself out pretty much every afternoon during the mid to late summer months when we get something called the southwest monsoon. And this is when we get higher humidities over this part of the country as a result of air flowing in low levels from the Gulf of California. So we don't really talk about the southwest monsoon in our class, but if you want to investigate this a bit on your own, you might want to just have a look at this, and you'll see that even though a lot of this area is desert, particularly in New Mexico, Utah, and Arizona, during the southwest monsoon, you can get very heavy rainfall in this entire area. And so here's an afternoon during the southwest monsoon where we get these Valley Mountain thunderstorms, and they're helped along by the higher dew points that are brought in from the Gulf of California. Okay, now I want to move on to wind shear. And wind shear is really, really important for those of you who are going to be pilots. And again, that is the lion's share of you who are taking this class. So let's talk about wind shear. There is both horizontal wind shear and vertical wind shear. We already talked about horizontal wind shear in this class when we talked about vorticity in chapters 12 and 13. In this context, when we're talking about thunderstorms and severe weather, we're going to be talking about vertical wind shear. Now, wind shear, just writ large, wind shear is defined to be the change in wind speed over the 0 to 6 kilometer layer when we're talking about vertical. But when we're talking about wind shear just in general terms, both horizontal and vertical, is the change in wind speed and or direction over some distance. That distance could be horizontal, like it is when we're talking about shear vorticity in chapters 12 or 13, or it can be vertical when we're talking about thunderstorms and severe weather here in chapter 9, as well as in chapters 14 and 15. So for our purposes, when we're talking about thunderstorms, we're going to be talking about wind shear in the 0 to 6 kilometer layer. So we're going to be talking about how wind speed and or direction changes in the 0 to 6 kilometer layer. Now, directional wind shear is really, really important when talking about severe weather, but it's also pretty complicated, and we're not going to talk about directional wind shear in our class. We're simply going to focus on speed shear in this 0 to 6 kilometer layer. Now, we're going to define wind shear or categorize wind shear as weak, moderate, or strong. Weak wind shear is defined to be wind shear that is less than 20 knots in this 0 to 6 kilometer layer. In better words, the wind does not change more than 20 knots in the 0 to 6 kilometer layer. And here's an example of weak shear. So you can see at the surface, the wind speed is 5 knots, and 500 millibars, which is about 6 kilometers up in this example, the wind speed is 10 knots. So the wind shear is actually only 5 knots. So the vertical shear is only 5 knots. So this is defined to be weak shear. Again, less than 20 knots. Moderate shear is between 20 to 35 knots. And I'm going to just jump right to strong shear. And strong vertical shear is defined to be any shear that is greater than 35 knots in the 0 to 6 kilometer layer. Now keep in mind that although I'm not talking about wind speed increase, this is really what I mean. Because friction is maximized at the surface, our slowest winds are going to be at the surface. And as we go up through the lower troposphere and we lose friction, as well as the fact that as we move above the friction layer, our pressure gradient force will still cause wind speeds to increase because of the pressure gradient that is directed from the tropics to the poles. So we're always going to get wind speeds increasing with height. It's just an issue of magnitude, whether it's a small increase and we have weak shear, or whether it's a very rapid increase of wind speed and we get large vertical wind shear. And here is an example of a profile where we get very, very strong wind shear. So again, you can see in this example, we have 5 knots at the surface, and we move up to 60 knots by the time we get a little bit higher than 500 millibars, or again, just 6 kilometers. So this is 55 knots of vertical wind shear. So what we're going to do is we're going to begin to talk about thunderstorms, and we're going to basically talk about organizational structures of thunderstorms. Now again, a thunderstorm is a thunderstorm in the sense that there's lightning, and the lightning leads to thunder, and it rains hard, and maybe we get hail. But the organization, in better words, whether the thunderstorm just organizes itself into random cells, or whether it organizes itself into lines, or whether we get supercell organization, that really comes down to the value of the wind shear and the magnitude of the wind shear. So we're going to really focus for the lion's share of the rest of this video about talking about thunderstorms that organize themselves as a function of wind shear. We're going to talk about single cell, multi-cell clusters, and supercells in this chapter. I'm going to leave multi-cell lines or squall lines for a discussion in chapter 14, even though it's listed here on this slide and the following slides. So we're going to talk about single cell, multi-cell, and supercell. And we'll start with single cell. So single cell thunderstorms develop in an environment with weak wind shears. So we're talking about wind shear again in the 0 to 6 kilometer layer that is less than 20 knots. So here is a base reflectivity radar image of single cell thunderstorms over Georgia, Alabama, and northern Florida, and southern South Carolina as well. So again, shear is less than 20 knots. There's no storm organization when we have single cell thunderstorms. These thunderstorms are driven, I just want to go back, these thunderstorms are driven entirely by convection. So what's basically happening on a day when we get single cell thunderstorms is, going back several slides, is that the energy from the sun is absorbed at the surface. We get intense heating of the near surface air via conduction. This air becomes buoyant, the atmosphere becomes stable, and then we get rising air parcels via convection, and these parcels are able to rise to the level of free convection, and we get single cell thunderstorms. But there's no organization. The thunderstorm activity is basically driven by intense convection during the afternoon, and so you get none of this in the morning, and as soon as the sun goes down in the evening, these thunderstorms fall apart because you lose the energy from the sun that drives the convection from the surface. So there's no storm organization. Now there is a distinct life cycle to single cell thunderstorms. So let's talk about the three stages. There's the towering cumulus stage, the mature stage, and the dissipating stage. And you'll see up here I have thunderstorm stabilizes atmosphere. And we'll get to this as I discuss the life cycle. Now the towering cumulus stage is actually pretty easy to understand because we've been kind of touching on it. We've been touching on it the entire video. And that is basically cumulus clouds that form as a result of surface-based convection. So what we have are parcels that are being intensely heated from the surface, they're becoming buoyant, and they're rising. Now, as a parcel rises, what will happen typically is that it will reach the lifting condensation level and we'll get a cumulus cloud. Now, these first cumulus clouds of the day don't have much vertical extent. And because, again, these volumes of air are not real parcels, what will happen is the drier air surrounding these first cumulus clouds of the day will be entrained into the cloud, and the cloud will evaporate. But the water from that cloud doesn't go away. The vapor actually goes into, the vapor that results from the evaporation just moistens the layer where that initial cloud formed. So when we get the next parcel rising as a result of surface-based convection, that parcel will lead to condensation in an environment that has a higher dew point, and the next cloud will be a little bit larger, it'll have a bit more of a vertical extent, and then it will evaporate as a result of entrainment. So what we see on a day when we have towering cumulus clouds is we actually have a sequence of clouds, cumulus clouds that develop, evaporate, develop, evaporate, develop, evaporate, but each cloud that develops ends up being a little bit larger and having a bit more vertical extent than the cumulus cloud that preceded it, because each cloud basically moistens this layer of the atmosphere a bit more. So as we go through the day, what will happen is because the environment is more conducive to cloud development, we will get greater vertical extent in our cumulus clouds. Our parcels are actually able to make it further up into the atmosphere, in the troposphere. And if this goes on long enough and the atmosphere is sufficiently unstable, then a parcel can reach the level of free convection and we'll get a thunderstorm. Now before I move on to the actual thunderstorm, what I want you to note is the vertical motions in our towering cumulus cloud. So because this is driven entirely by convection, what you'll see is that our vertical motion is dominated by what I refer to as what I call updrafts. And this is common terminology, by the way. So we get updrafts of air into our towering cumulus clouds as a result of this surface-based convection. You'll also notice that we have a 32-degree isotherm going through our cloud and also starting basically in the environment and ending in the environment. And what you'll see is that the 32-degree isotherm is actually a little bit higher in the cloud itself, And this is because of the latent heat that is being released as our vapor is condensing to form this cloud. So the latent heat release in the cloud actually leads to a slightly higher temperature inside the cloud than in the surrounding environment, and you can see this reflected in this little bump upward in our 32-degree isotherm. Now the towering cumulus stage can go on for a good long time. So the first cumulus clouds in the morning may actually start to form 9:30, 10 o'clock in the morning, and it may be 4 or 5 o'clock in the afternoon before the single-cell thunderstorm actually produces a thunderstorm. So this can go on for a good long time. I'm putting 4 to 6 hours here. It can even be longer on a day when you get a thunderstorm. So this goes on a long time before we finally get parcels that are actually able to make it up to wherever it is that the level of free convection is located in the troposphere. Now, once the parcels reach the level of free convection and we get a thunderstorm, then things begin to get more interesting. And not just because we have a thunderstorm, but in the context of the thunderstorm and how it actually impacts the vertical temperature profile in the troposphere, there's a lot going on during this mature stage. So what I want you to notice, obviously, is that our cloud has a much greater vertical development. So once the parcels are able to reach the level of free convection, they accelerate upward very quickly, and all of a sudden we go from having towering cumulus clouds to a cumulonimbus cloud. So here's our cumulonimbus cloud. Cumulonimbus simply means a cumulus cloud that is producing precipitation. That's what the nimbus part means. So it's typically a thunderstorm, but it doesn't have to be. So a cumulonimbus cloud is producing rain, and you can see that our rain is falling out of the cloud right here. So rain actually has an impact on our vertical motions, and if you take a look where the rain is located, you'll see we have a lot of downward pointing arrows, and these are downdrafts. So the rain actually leads to the formation of a downdraft. So this is downward moving air. We still have an updraft beneath the thunderstorm, so we still have convection going on in this particular area beneath the towering cumulus cloud, the cumulonimbus cloud, but the rain is leading to the formation of a downdraft. Now, if you took my weather and climate class or my weather studies lab class, I talked about why these downdrafts form in detail. And I'm just going to mention the two contributing factors that rain produces downdrafts here, but you may need to read up on this a bit more, either if you've taken my classes and need to refresh your memory, or if you're not taking my classes and you need to really just learn about this. But basically, there are two things going on here. The first is that the rain, when it falls from the cloud, it's physically dragging air down with it. So the air, as a result of friction or drag, is actually pulling air down with it, and that contributes to downdraft formation. Also, as the air falls beneath the cloud, it is falling from an environment in the cloud where the air is saturated to an environment beneath the cloud where the air is subsaturated. So what we see where the air is subsaturated is that not only is the air falling into this air, not only is the rain falling into this air where the relative humidity is less than 100%, we also get evaporation in this air as well because it's subsaturated. Evaporation is a cooling process going back to geography 1215, 1260. And so where we get evaporation, we get cooling air. As the air cools, its density increases, and the air will begin to sink on its own as a result of its increased density. So downdraft air is formed as a result of frictional drag and as a result of evaporative cooling. And so if we take a look at our 32-degree isotherm again, what you'll see is a more pronounced bump upward in our towering cumulus cloud, our cumulonimbus, because the parcels are rising much more quickly, the rate of condensation is now much greater, and because of that fast latent heat release, we're getting a bigger bump in temperature inside the cloud. You'll also see that the 32-degree isotherm is depressed outside of the cloud, where the rain is falling into the subsaturated air as a consequence of this evaporative cooling. So the evaporative cooling is actually leading to the suppression, the vertical suppression of this 32-degree isotherm to a lower altitude. So as this downdraft air reaches the surface, what it will do as it hits the surface, it will begin to spread out horizontally. So you can see that the downdraft air begins to spread out both behind and ahead of the storm. And this dashed line is actually meant to depict a boundary between this colder downdraft air and the warmer air that is on either side of it. And so because this air is colder, it spreads out kind of like maple syrup on a tabletop, and you can see this spread right here at the surface. So what happens ultimately is that the surface air is cooled because of this downdraft air basically reaching the surface. So as the surface cools, as the downdraft reaches the surface, as cold air reaches the surface air temperature decreases, and the environmental lapse rate decreases as well. Now, you guys probably all know this already. If you think about your experience with thunderstorms, the last thing that you probably experience before the rain begins is that the wind picks up and the temperature drops really, really quickly. So what you're experiencing with that pickup of wind speed is the downdraft air as it spreads out horizontally ahead of the thunderstorm, and of course that downdraft air has been cooled by evaporation. So as that cold air reaches the surface, it spreads out, the surface temperature decreases, the environmental lapse rate decreases, and the atmosphere becomes more stable. So during the mature stage, which lasts about 30 to 45 minutes, the thunderstorm, the single-cell thunderstorm, is stabilizing the atmosphere. Now, as the atmosphere stabilizes, you basically are losing the source of convection. If the atmosphere is stable, then you're going to lose your convection and you're going to lose your updrafts. And so what we see as the atmosphere matures and we move towards the dissipation stage is that our updrafts basically are almost completely gone beneath the thunderstorm. And now the vertical motion is basically dominated by downdrafts that are caused by drag and evaporative cooling. You may have some upward motion still in the cloud itself, but you have lost your surface-based convection because the surface is now cooled by the rain and the downdraft. And so once you lose your surface-based convection, the single-cell thunderstorm basically falls apart. So if we take a look at all of this together, what we see is that the single-cell thunderstorm forms as a consequence of instability and convection. The thunderstorm, once it matures, restores stability to the atmosphere, and then once that atmospheric stability is restored, the thunderstorm dissipates, it falls apart. So the thunderstorm is a consequence of instability, and then it returns stability, and once it's done its job, it's gone. So the dissipation stage might just be another 15 to 30 minutes before the whole thing is gone, and you basically end up with a glaciated cloud that's not producing precipitation at all. So if you take the whole thing together, the entire life cycle might take the entire day from where you get that first cumulus cloud to where the single cell dissipates. But once you actually reach the mature stage, you're talking about less than an hour, generally speaking, from maturation and rain to complete dissipation. So they don't last long. So here is a sideways view of a single-cell thunderstorm. And again, when you get this mature stage in a weakly sheared environment, what happens is that the gust front, and this is basically, I'll talk about gust front in a moment, I'm getting ahead of myself, but basically the downdraft air is able to accelerate and move very, very quickly out in front of the single-cell storm. So what we see, I'm going to actually define a gust front now before I really get too far ahead of myself. The boundary between the downdraft air, which is cold, and the hot, unstable air ahead of the thunderstorm, the boundary, which is right here, is called a gust front. So the gust front is right here. It acts as a cold front that is basically generated by the downdraft air of the thunderstorm. And in a weakly sheared environment, what we see is the gust front basically moves very, very far out ahead of the single-cell storm. So while it acts as a cold front, and it's able to wedge this warm, unstable air ahead of the storm upward, what we see is that this unstable air is not actually able to be wedged up into the single-cell thunderstorm to maintain its integrity so it can continue to exist. Instead, what we see is that we get new cloud development well out ahead of the single-cell storm. Now, this new cumulus cloud development may ultimately lead to another thunderstorm, but the single cell that produced it is not going to be able to benefit from this warm, unstable air being forced upward, and it's going to dissipate. So we get these unrestrained outflow boundaries, which is the actual downdraft air, and the gust front, which is the boundary itself. And it cuts off the supply of warm, humid, unstable air into our single-cell storm. So the surface air beneath the single cell is cooled by the rain and the downdraft, and again, the environmental lapse rate beneath the thunderstorm decreases. Rising parcels become colder in the environment because the atmosphere is stable, the convection ends, the updrafts disappear, and the thunderstorm dissipates. So this is what we see, the single-cell thunderstorms. We get these, by the way, over Ohio many afternoons during the summer when the weather is hot and humid here at the surface. So this is a very, very common phenomenon. These are the types of days when you might have a thunderstorm in Bowling Green, but not in Findlay. You might have a thunderstorm in Toledo, but not in Perrysburg. So they're relatively localized, less than a county in size, and again, they are randomly scattered over the landscape. All right, let's move from single cell to multi-cell clusters. Multi-cell clusters actually are clusters of thunderstorms that have some organization, and they form in environments that have moderate shear. Now remember, moderate shear means that the wind speed is increasing in the 0 to 6 kilometer layer from between 20 and 35 knots. So the vertical wind shear in the 0 to 6 kilometer layer is 20 to 35 knots. So what we see with a multi-cell thunderstorm cluster is that we have this moderate shear, and what the moderate shear does is it tends to restrain the gust front. Now remember that you've got gust fronts that are moving out in directions, not just in one direction from the thunderstorm. Now in this particular set of schematics, it's not showing the gust front that's moving out ahead of this storm. But note that the directional shear is in the same direction ahead of the storm as the gust fronts. We tend to get unrestrained boundaries on, or outflow boundaries on that part of the thunderstorm where the outflow boundary is moving in the same direction as the winds. But if we take a look behind the thunderstorm, as the thunderstorms are moving from left to right and our winds are blowing from left to right, what we see is that the outflow boundary, the gust front, basically behind the storm is being restrained by this stronger wind shear, by this more intense wind shear. And so what's happening now is that because of this restrained gust front, the unstable air that is basically right here is being fed into the thunderstorm, and so we're getting acceleration of air upward, and we're getting the development of a new cell. So here is basically cell 1, which is dissipating, cell 2, which is mature, and cell 3, which is beginning to form as a result of this outflow boundary gust front behind the storm, feeding new air up into the cluster, which is reaching the level of free convection, and so we're getting new thunderstorm development. So what we see in this case is that as the entire cluster is moving off from left to right, we're getting back-building thunderstorms. So what we get is a thunderstorm moves over an area, a new thunderstorm forms, moves over the same area, and so on. So these multi-cell clusters actually provide us with our first real severe threat. Now, when we're talking about severe weather, technically, severe weather in the eyes of the National Weather Service is really all about extreme winds, large hail, and tornadoes. But when you're talking about the extreme weather, I think you've got to include flooding as well, because flooding really does impact people and it really is disruptive. So we get something called training of cells when we get this back building. So think about a train where a train is moving down the track and you've got car after car after car moving over the same track. So when we get training thunderstorm cells, what we have is this multi-cell cluster that's basically moving in one direction, and these back-building cells are basically training over the same areas. So these areas that experience training are getting thunderstorm after thunderstorm after thunderstorm. And this can go on from an hour to several hours. And so the longer the training goes on, the more thunderstorms continue to form over the same areas, the more severe the flooding will be. So flooding is really the main threat from these multi-cell clusters. And so here's just elapsed time to show this backbuilding continuing and this continuing dissipation of cells on the front end, and then backbuilding and training going on the left side of the diagram. And so again, this process continues. So if we take a look at this particular set of base reflectivity images, we've got some single cell storms on the southern end, and then we've got a couple of multi-cell clusters forming on the northern end. Now I want you to just note that we're taking a look at several counties here. So this is actually a couple of hundred miles of distance north to south that we're looking at. So on the northern end of this particular map, the wind shear is a little bit stronger and we're getting some organization of our thunderstorms. And you'll notice that the gust fronts, which is basically the blue right here, that they're hewing really, really close to where the actual thunderstorms are located. Where we have weaker shear, less organization, and we're talking about single cells, you'll see that the gust fronts are much, much further out ahead of our single cells. So here's where we have unrestrained boundaries, gust front boundaries, with lighter wind shear, weaker wind shear, and where we have our stronger wind shear, our gust fronts really do hew much closer to the thunderstorms themselves. So again, just because we have gust fronts, and you can see it really clearly here, doesn't mean that you necessarily have thunderstorms going on at this moment. You can see a little bit of green here, a little bit of development, so maybe a little bit later on you get thunderstorms. So here are single cells, multi-cells, and their associated gust fronts. If you take a look a little bit later, you'll see that we still have our gust front boundary well ahead of our single cells to the south. And here is our much further developed multi-cell cluster with back building. And you'll see that our gust fronts are really restrained all around our multi-cell cluster. And you'll note that the movement is basically from west-southwest to east-northeast. And so as these cells are back building, they're basically moving or training over the same area. Now it's fairly small. I mean, it's less than a county wide here, but within this training area, you can get very severe flooding. And here is a nice example of back building thunderstorms in a multi-cell cluster over Ireland, which you might not think of as a location for thunderstorms, and these may not actually be producing thunder and lightning, but they're obviously convective. And you can see the back building going on from our best developed mature cell here on the left to our back building in this case on the right. All right, I'm going to move on from single and multi-cell. And by the way, I just want to indicate here the actual updraft strength, which is linked to severity, as well as the threat to severe here as well. I didn't really talk about that because I'm so focused on wind shear. Our last type of organization I'm going to talk about in Chapter 9 is supercell thunderstorms. Now, supercell thunderstorms, probably many of you have heard of them. These are the ones that almost always produce severe weather and are often associated with tornadic activity. So I'm going to touch on supercells here. I'm going to talk more about them in Chapter 14, and I'm really going to talk about them a lot in Chapter 15. So this is just our first treatment of supercell thunderstorms for our class. Supercell thunderstorms form in an environment with strong vertical wind shear. So that means that the vertical wind shear in the 0 to 6 kilometer layer is greater than 35 knots. So again, forming within a strongly sheared environment. When we get supercell thunderstorms, the lower levels of the troposphere are moist and unstable, and we typically get this instability forming after an extended period of sunny conditions. So the heating precedes the supercell outbreak. Now, note that these conditions are very similar to what we have when we get a single cell thunderstorm day. But the big difference between a day with single cells and a day with supercells, excuse me, is the wind shear. So remember, with single cell thunderstorm days, our wind shear is less than 20 knots, and on a supercell day, our wind is greater than 35 knots, often much greater than 35 knots. Now, if we take a look at a sounding of a day with supercell thunderstorm activity, and we take a look first at our vertical temperature profile, and this is our red profile, you'll see that the environmental lapse rate in the first couple of hundred millibars above the surface is pretty large. And you'll also notice that the dew points are also pretty large as well, and the dew point depressions, in better words, the distance between the temperature and the dew point temperatures is fairly small. So not only is the atmosphere unstable, but it's also pretty humid. Also, if we take a look at our vertical wind shear, you'll note that the wind shear is large. So in this hypothetical situation, we have surface winds southwest at 10 knots, and then by the time we get to 6 kilometers, we're talking about west at 70 knots. So this is an example where the vertical wind shear is 60 knots in the 0 to 6 kilometer layer. You'll also notice that at about 2 to 3 kilometers above the surface, we get what we call a V-shaped temperature dew point signature. So we get a V shape in our profile. And this is a really common signature that we see on supercell thunderstorm days. And I'm just going to put it in a little oval here so that you can see it really clearly. So in our V, where we get our V profile, you'll notice that we get a fairly shallow temperature inversion. Remember that inversions are extremely stable. So we get a very shallow, very stable layer, typically 2 to 3 kilometers above the surface. In this same layer, what you'll see is that the air really dries out, so the dew point temperature really drops off. So we get a stable and very dry layer above this unstable layer. Now, this capping inversion, which meteorologists will call this a capping inversion, what the capping inversion does is it basically caps the convection to the layer beneath it. So if, in this example, our inversion is located at 700 millibars, what we'll see is that the convection is basically capped beneath this inversion. So the vertical motion is basically not able to penetrate this inversion, and so all the energy from the sun, all this convection basically is building up beneath this capping inversion. And so what happens ultimately is that there'll be some sort of a trigger that enables our parcels to actually get through this capping inversion and erase it. It can either simply be that the convection is so intense that it's actually able to break through. A front can be driving through the area, and that front will provide an extra lift that will actually enable our parcels to actually break through this capping inversion. We can actually get an outflow boundary from thunderstorm activity that is upstream of this location, and that can provide the extra boost in vertical velocity. There are a number of ways that we can actually get parcels to actually break through this capping inversion. But when it finally happens, because of the amount of energy that is built up beneath this inversion, we typically get extremely explosive growth as a result of all of this upward motion. Parcels very quickly reach the level of free convection, and then we're off to the races. When we get supercell thunderstorms, these thunderstorms are discrete. They are cells versus being organized along some sort of a line that we would see with a front, so a squall line or a line along a front. So supercell thunderstorms are discrete, but they're also incredibly violent and they're extremely dangerous. We typically get rotation within something called a mesocyclone. Meso means medium or medium scale. So within our supercell thunderstorm, we'll typically see a region where we have rotation over a fairly small area that is counterclockwise, and we refer to this cyclonic circulation as a mesocyclone. So we'll get a mesocyclone that is associated with our supercell thunderstorm, and the mesocyclone is where it is that we look for tornadic development. So what happens is air is swept up within the mesocyclone, it very quickly rises, reaches the level of free convection, and it accelerates upward. So we typically will get not just very strong upward motion, but this updraft is typically rotating along with our mesocyclone. So this is kind of the vertical extent of our mesocyclone. We get explosive development, and we get something called a rotating wall cloud, which we'll take a look at in a few slides. And then we typically will get tornadoes when they do occur, lowering from our rotating wall cloud. Here's an example of supercell thunderstorms on a day in February in 2009. This was a day of a pretty big tornadic outbreak in the southeast U.S., and you can see them over Mississippi, Alabama, Georgia, South Carolina, and northernmost panhandle of Florida, and even into Louisiana, although we do have a little bit of a linear structure here in Louisiana. So let's take a look at this schematic map of supercell activity over Tornado Alley. So Tornado Alley, which we'll discuss in greater detail when we get to chapters 14 and 15, basically extends from northern Texas up through the southern and central plains into southern South Dakota. So basically, this is the heart of Tornado Alley right here, from southern Nebraska through Kansas and Oklahoma. So here's our setup. And what I want to do is just focus on the warm sector of this particular low. Now, if you probably know that tornado season, in terms of the climatological peak in tornadoes across the United States and Tornado Alley, occurs during the spring. During the springtime, we get something called lee-side cyclogenesis. We get a lot of surface low pressure. Now, these are large-scale lows that form typically over southeast Colorado, and then they move off to the northeast with time. These lows form, they're very dynamic. The structure of the upper levels is very dynamic. We got large vortexes. We typically have a pretty really well-developed jet stream with a jet streak embedded somewhere within it. So there's a lot going on here on the large scale to give us this large-scale mid-latitude cyclone. So here's our mid-latitude low, and in this case it's just focused on the Colorado-Kansas border. Here's our cold front, here's our warm front. And what I want to do first is I just want to focus on the warm sector of this low. If you take a look at the counterclockwise and inward directed circulation at the surface around this low, what you'll see is that in the warm sector, we have air at the surface that is originating both over Mexico and over the Gulf of Mexico. So as a result of the air coming off of these two different masses at the surface, water and land, the air will have different characteristics. Now, it's warm. It's coming out of Mexico. It's coming off the Gulf of Mexico. So this is tropical air. All of this air in the warm sector is tropical. But the air that originates over the Gulf of Mexico is maritime tropical. In better words, it has a high vapor content. It's humid, high humidity. So maritime for humid, tropical for warm. The air that's originating over Mexico is also warm, but it is continental. It is dry. So we have continental tropical air. So we have two different air masses within our warm sector, both tropical, one maritime, one continental. And that will lead to something called a dry line. So this boundary right here is a dry line. So the dry line basically looks like a front. If you take a look at the symbology of the dry line, it looks a lot like a warm front in terms of the semicircles. But a dry line is not a classic front because there's really no temperature difference across the boundary. What a dry line does is it marks the boundary between air masses that have two different humidity characteristics. In this case, maritime humidity characteristic in our air off the Gulf of Mexico and dry or continental characteristics for the air that's originating over Mexico. Now, dry lines are important because it turns out that continental and maritime air have different density characteristics as a result of the different vapor characteristics. And so what we see is that given uniform temperatures, humid air is actually less dense than dry air. Or to put it the other way, dry air is more dense than humid air. So as our dry front boundary advances from west to east on this map, what it does, and this is a subtle boundary, it's not strong like a cold front, what it does is it provides a little extra boost upward for the air along the boundary. So we typically will see supercell development along this dry line boundary because we also have the jet stream blowing above our boundary. So we have convection going on in the sunny air. We have humid air that's being forced upward as a result of our dry line and also rising as a result of convection in a strongly sheared environment, and that will lead to supercell development. So lifting along and ahead of the dry line will lead to very rapid acceleration of air to the level of free convection, and up it goes. Now, what we see when we have supercell development along a dry line is that we won't get an organized structure where we have thunderstorms all along the line because the lifting along the dry line is pretty subtle. And so the lifting in some parts of the dry line, along some parts of the dry line, will not be sufficient to get parcels to the level of free convection, while on other parts of the dry line, it's sufficient to get the level of free convection and we'll get a supercell. And so what we'll typically see is a quasi-linear organization. We'll have the supercell here, maybe another one here, another one here. So you can connect the dots of the supercells and get a line, but the supercells will not be in a solid line along the dry line. So if we focus on the supercell from a side, just to give you an idea of what it looks like, here are our weak low-level winds, our strong high-level winds. You'll notice that there is directional shear as well as speed shear, but again, we're just going to focus on our speed shear. Our updraft is occurring within a mesocyclone, which you can't really see really well here, but here's our updraft basically going up into the thunderstorm, and this updraft will typically be rotating. So we have strong wind shear greater than 35 knots, a rotating updraft into the storm, and then we get our wall cloud. So if we take a look more really straight into it from the surface, you'll see our updraft again. Here's our downdraft now that's actually as a result of the rain and perhaps hail that's coming out of our thunderstorm. And you can see what we call a wall cloud right here that's beneath our updraft. Now the wall cloud is actually part of this rotating updraft, but because the air is rising so quickly, it's very quickly expanding and cooling, and so you'll see that because of this rapid cooling, we'll get some condensation beneath the main cumulonimbus cloud, and this is our wall cloud. And because the updraft is rotating, the wall cloud also typically rotates counterclockwise as well. So we get intense downdraft and outflow with this falling rain and hail, and if it's really, really strongly coming down in terms of the downdraft, we sometimes will call this a downburst. And here's a picture of a supercell with a wall cloud. Here's the supercell, here's a wall cloud. You can see that the actual hail and the heavy rainfall are not actually falling out of the wall cloud itself. It's actually falling out of the main thunderstorm tower, which is actually located a little away from the mesocyclone and the wall cloud. And we'll see this in the next slide or two when we take a look at the supercell from above. I just want to point out, although I'm not attributing the actual source here, I did not take this picture. I shamelessly stole this from the internet, as I do with most of my pictures. So just note, this is not mine. I do not want to take credit for this picture. Okay, let's take a look at the supercell from above. So what I want to just point out here in terms of the coloring is that the shading here is meant to mimic what we would see on a base reflectivity radar map. So the grays indicate that there's really nothing falling out of the sky in terms of precipitation. The blues indicate light precipitation, and then we go upscale in terms of our reflectivities, all the way to our oranges and our reds here, which indicate heavy rainfall and hail. So here's our supercell from above. So let's talk about the characteristics of the supercell itself. First of all, the heavy rain and the hail is falling from the main tower of the storm. So even though we're getting really rapid updrafts in our mesocyclone, which I'll talk about in a moment, what happens is that as this air rises basically out of your screen, what it's going to do, it's going to encounter upper level winds that are coming out of the southwest. The upper level southwesterlies will take our rotating updraft and then they'll push it off to the northeast so that it basically aligns with our upper level flow. And as a result of that, what we'll see is that the heaviest rain and hail is actually occurring to the northeast of the mesocyclone. So this is the main tower of the thunderstorm. So we have heavy rain, large hail, and as a result of this, we get very, very powerful downdrafts that are produced by our heavy rainfall and hail. And so these streamlines, these arrows are meant to indicate both the downdrafts and the outflow of our downdrafts once they reach the surface. And then what they will do is they will produce a pretty well-defined outflow boundary. So this is our gust front that's produced by the main tower of the thunderstorm. And we refer to this downdraft air as the forward flank downdraft. And then here is its gust front. So these winds are extremely strong, very, very much rain-cooled air, and a really well-defined boundary. By the way, the movement of the entire thunderstorm, which is determined by the upper level flow, is almost always southwest to northeast. So here is our main tower and the forward flank downdraft. Now, what we see is that the air ahead of the storm is swept into the rotating updraft along the forward flank of the storm. So I've put in this red arrow. You won't see this in the text when you're reading your book. I added this, as well as this verbiage right here. So the air is swept into the rotating updraft along the forward flank of the storm and our rotating mesocyclone. So here's our rotating mesocyclone, and you can see the counterclockwise circulation of our rotating mesocyclone. So the rotation basically will cause the clouds and the precipitation from the main tower to be swept along the circulation. So this is basically thunderstorm air that's being swept along the mesocyclone. You can see our radar reflectivity is basically being twisted around the mesocyclone. And so this rotation of air will produce our rear flank downdraft. This is basically produced from the downward motion caused by rain here, as well as our hook echo. So the hook echo is basically seen on base reflectivity, and this is basically the thunderstorm air and its precipitation that's being swept around basically the west and south side of our mesocyclone. And then what we get is our rotating wall cloud with our rain-swept air in the mesocyclone, and our tornado, which is indicated by the T, is typically located right along the tip of our mesocyclone. So we've got our forward flank downdraft, our rear flank downdraft, air being swept into our rotating mesocyclone, which then very rapidly rises and is swept up into our upper level southwesterlies to produce our heavy rain and hail in the main tower of the thunderstorm. Again, with our tornado right on the tip of the hook echo. And again, we've already seen this once or twice in our class and our videos. Here's an example of a hook echo, and this is with the really historic May 3rd, 1999 F5 tornado that flattened Moore, Oklahoma. And so you can see the main tower of the thunderstorm, and here is our hook echo. And so our radar signatures, if we take a look at base reflectivity, here's our hook echo. Now, if we take a look at other radar signatures, here is an example of base reflectivity on the right and base velocity, or on the left, pardon me, and base velocity on the right, so we can see what a tornadic thunderstorm looks like on both reflectivity and velocity radar. Now, this is an example of a tornado that occurred to the northeast of the Melbourne Beach, Florida Doppler radar. And in this example, you can see that we don't actually have a hook echo. So it's important to know that not every tornadic thunderstorm produces a hook echo. This is a tornado that formed within a fairly large field of rain and thunderstorms, and so the hook doesn't actually come out on this particular example. So if we were just relying on base reflectivity, meteorologists wouldn't see a hook, and they might not actually release a tornado warning or put out a tornado warning. And so this is an example where without Doppler radar, the public would really be at high risk of damage and death as a result of a tornado that was not part of a hook. So if we take a look at our radar signatures, base velocity, no hook. If we take a look at our, base reflectivity, no hook. If we take a look at base velocity, what you'll see where the tornado is located is that there's a distinct shift in our velocities. Now remember, and we don't actually have our velocity key on this, but our green velocities indicate that we have movement toward the radar, and our red colors indicate that we have movement away from the radar. So we actually have a phase shift over a fairly short area here, where we go from having motion toward the radar to motion away from the radar. And we call this phase shift a tornado vortex signature. It's not just about the phase shift, by the way. It is really about how much our wind speed changes in terms of our vector velocity toward and away from the radar. So if we have very strong winds toward the radar here and away from the radar here, the actual net change in wind speed in terms of direction is quite large, and we'll say that we have a tornado vortex signature. We'll talk about this later on in chapter 15. So we have a change in wind direction relative to the radar site, and you can see now that if I put these yellow arrows in, where we have our green, we have motion toward the radar. Where we have our red, we have motion away from the radar. And if we put a little pinwheel in here, what you'll see is that this very, very rapid change in motion over a short distance will actually cause the pinwheel to rotate counterclockwise. And so we'll actually get counterclockwise rotation at cloud level. Now, let me just say a little bit more about this before I move on. And that is that we will sometimes pick up a tornado vortex signature maybe 30 to 45 minutes before we actually get rotation at the surface and we get the touchdown of a tornado. So seeing this tornado vortex signature at cloud level gives the National Weather Service sometimes lead time of 30 to 45 minutes to notify the public that there's an imminent threat of a tornado and for people to actually get to safety. And this lead time of 30 to 45 minutes sometimes, it may not seem like a lot of time, but it really is. And it's enough time once those sirens go off for people to actually get to safety and to shelter themselves. And so Doppler radar and our ability to actually increase our lead time and to warn the public has really led to a dramatic decrease in the number of fatalities in the US as a consequence of tornadic activity. Here are some examples of a tornado. And again, this is our May 3rd, 1999 tornado that flattened Oklahoma. So this is a really nice example of base reflectivity on the top and base velocity on the bottom. And you can really see the tornado vortex signature really, really well. That's located right where you've got your hook as we move through time. And these brighter colors indicate faster motion. So you can really see where we got our pulse in our strongest wind speeds, our strongest rotation with this particular tornado. I also have a couple of YouTube links below so that you can take a look at a couple of videos that I think that are particularly good in terms of showing tornado. These are videos where the storm chasers really did a good job of keeping their cameras still. So it's not really shaky, and so you can really see the development and the evolution of these tornadoes really well with these two links. Okay, before I end the video, and this is just because the chapter focuses on this a little bit and there are one or two questions in the exercises or lab, I'm going to talk about lightning. Now, as I do this, I want you to understand that my knowledge of lightning is really not good. It may be just about 5 minutes better than yours, and that's it. So I'm just going to say a few things about lightning and then finish this off. And this is just so that you can actually answer the questions in the exercises. So there's a National Lightning Detection Network. So here's an example of thunderstorms over the southeast. And this is actually kind of an old image. So I suspect that the imagery with the detection network is actually much, much better than it is now. But we actually are really very capable of detecting lightning activity with thunderstorms. Now, my very basic understanding of lightning comes down to the two-layer model of charge separation in the cloud. When we don't have thunderstorm activity, the Earth's surface basically serves as a universal ground. So it's basically an infinite ground for electrons, and so it's negatively charged. When we have thunderstorm activity, the two-layer model, which is actually very simple and really basic, the most basic model, basically shows that there's charge separation beneath the thunderstorm. So just beneath the thunderstorm, we get positive charge at the surface, and we get negative charge in the base of the thunderstorm. And so what happens when we get lightning is we basically get a redistribution of charge where we get a flow of electrons to the surface, and a lightning strike will reestablish negative charge at the surface. And during the thunderstorm, what we'll see is that this charge separation will occur over and over again, and we'll get more and more strokes of lightning beneath our thunderstorm. There are many more complicated models of charge separation, not just between the thunderstorm and the surface, but within the cloud itself. So for those of you who are interested in lightning and this charge separation, unfortunately you're going to have to do more research on your own in the internet. There's a lot of information there. This is really complicated, which doesn't mean that I can't comprehend it. It just means that my area of expertise, which is also very complicated, is not in lightning. But just understand, if you begin to investigate this, it will get complicated pretty quickly. So give it a shot and have a look at it. I'm just not terribly interested in the details of lightning, and that's why my knowledge is kind of low when it comes to this stuff. Now, in your exercises, you're going to be asked to calculate both the speed of sound as well as the distance between lightning and where you are, to calculate how long it takes for thunder to reach you. So in order for you to calculate the time it takes for thunder to reach a location where you might be, you first have to know the distance from the cloud to you in meters, and then you have to divide that by the speed of sound. The speed of sound is a function of temperature, and you'll read about this when you're doing your exercises. So just know that sound is temperature dependent, and the distance from where a lightning strike occurs to where you are is a function of the speed of sound. Also know that the reason that there's a difference between when you see lightning and when you hear the thunder is because when you see lightning, that light is traveling basically at the speed of light, which is 186,000 miles a second. Thunder, on the other hand, is moving along at the speed of sound, which is around 300 meters or so per second, or about 1,000 feet per second. So while light is moving at the speed of light, 186,000 miles per second, sound is only moving about a mile every 5 seconds. And so the further you are away from a lightning strike, the longer it's going to take for the thunder to actually reach you and for you to hear. So that's why there's this difference between seeing the lightning and hearing the thunder. And that's all I really want to say about thunder and lightning. Again, just remember, these questions are for distance students who are taking Geography 2130. So here are the lab questions for the distance students. Again, if you're watching this video and you're a face-to-face person, you need to actually take a look at your PowerPoint, the last slide, to see what the assignment is for you and your group. For those of you who are taking this distance, remember that if you have any questions, feel free to post your questions to the discussion board, or feel free to ask me live during my office hours on Zoom. But that's it. That's all. That's everything I want to say about Chapter 9. I'm going to end the video now. I'll post it on YouTube, and I'll let you know when it's ready for you to view.